Hello everybody and welcome back to another video where today I will be teaching you practically rocket science. It's how much energy is required to launch an object from one point to another significantly further away, especially compared to the distance to the center of the planet. So let's say you start off at a distance of r naught away from the planet, and you want to get to this distance, which we will label as RP. And you are wondering how much work is required to get there. So using the general equation, which is that the potential energy for gravity, or the gravitational potential energy is equal to mgh, does not work here because g is not constant in this equation. As g changes as you go up from here to here, this delta r, which would be your h, just doesn't work the same right here. So we cannot use this equation, sadly. However, today we will be deriving this equation. So first, let's start by looking at the graph of force times the distance away from the force, which we are going to call radius, but this is force of gravity. So since we know Fg equals g times the mass of the object times the mass of the planet divided by the radius squared, and this is all a constant with respect to the radius, this is going to be similar to the graph of 1 over x squared, but however we're just using r. Now, since we have this equation, F times displacement equals work done in a system, we know that the area under this graph, let's say this is RO and this is R1, is going to be equal to the work done. As this, let's assume this was a just square, ignore this part, this area would be equal to F of G times R, which is equal to work. So in order to find this area, we are going to be using calculus and integration. So we are going to be integrating the equation for work. So let's write out the derivative of energy with respect to, we could just write it like this. dE over dr equals force of gravity, which is equal to this equation right here. Now, since this right here is a constant with respect to the radius, or the distance from the planet, I don't know why I keep calling it radius, we are going to write that this is equal to c, just to make writing this out a lot easier. So when we multiply both sides by dr, we get dE is equal to c times 1 over r squared, or just c over r squared, times dr. Then we are going to integrate both of these from r r1 to r naught to r1. So we have r naught, r1, then we have r naught, and then r1. So this integral right here is just equal to the work done in the system, since that is the change in energy, and work is equal to change in energy. So now we just have to tackle this piece right here. Since that is a constant with respect to r, we can pull that out of the integral, and we can just integrate this equation, 1 over r squared, which is also equal to r to the negative 2 times dr. Now we are going to be using the power rule for integration. So we have that this is equal to r to the negative 2 plus 1 over negative 2 plus 1, which is equal to this constant times negative 1 over r from r naught to r1. So now we can write this all out. Work is equal to C times integral times this integral expression, which is equal to negative 1 over r from these bounds, r naught, r1. So now we could plug these in right here. So we get C times 1 over r1. This is negative, and then minus negative, since the equation for an integral, this becomes a plus, and then we get RO, which is all multiplied by this constant. Now, if we want to simplify this, we can multiply this side by RO, and then multiply the top by RO. And we can multiply this part by R1, and then we can multiply the bottom by R1. And then we can simplify the denominators and get work is equal to, we'll replace the constant now with GMOMP, where this is mass of the planet, this is mass of the object, times R1 minus RO over the product of the distances. Since R1 minus RO was established as this change in radius, we will be calling it that, the change in the distance. So we get this equation. The work is equal to G M object times mass of the planet times the change in radius divided by the product of the radii. Now, in the next video, I will be applying this to some problems and showing you how to calculate the escape velocity of an object, as well as doing just basic physics with it. This is a very useful equation and very good to understand conceptually. And it's a pretty simple one. It doesn't take that much work to know. You don't need that many complicated ideas, just a little bit of calculus, and you're set. Thank you for watching, everybody. I hope you enjoyed this video and learned a lot. Please like and subscribe, and I will catch you in the next one. Thank you for watching.